So we'll look at a couple of other ways of describing a topology, but more importantly introduce a couple of terms which will turn out to be very important as we go ahead. So first of all, we have defined basis, and I mentioned that we will also have a notion of a sub-basis. Okay, so a sub-basis, so let's say if X is a set and delta is contained in the power set of not S but X, then delta is a sub-basis for maybe a specified topology omega or for some topology omega. If let's look at the corresponding collection of finite intersections, V1 intersection Vn. So if we look at these intersections V1, V2, Vn, where each Vi is in delta. So I look at finite intersections of sets in the sub-basis if this is a basis, and again of omega, for omega. So you can say for some topology or for a specific topology. So a sub-basis means if I took finite intersections of that, then you get a basis. Now being a sub-basis is almost automatic. So here's the following result. We say that we see that delta is a sub-basis if and only if the union of the sets in delta, so let's call them V in delta of V, is all of X. So this almost trivial condition is all we need. So this is very convenient. Of course, we have to then work with finite intersections of these when we actually use the topology, unlike a basis where we know it more explicitly. But still, so well, let me just say idea of proof. It's really quite simple. First of all, being a basis means the union should be all of X. And indeed, it's very easy to see that union of V in delta of V is actually the same thing as union of, let's say, W in B of W. Namely, any element, single sets are already in finite intersections. So if everything is in delta, then it's in B. And the other way inclusion is because this is each of these intersections is at least is contained in V1, for example. So it's easy to see this. And so this will tell you that if B is a sub-basis, then this is true, and hence this is true. On the other hand, if given this condition, we have one of the conditions of being a basis true, W in B. And what about the other condition? The other condition of being a basis is that we have finite intersections. So finite intersections of elements of B. So these have to be unions of elements of B, but in this case they are actually in B, literally on the nose. So there is no, that is very easy to see, because if we are looking at, for example, two of them, in fact you need to look at it only for a pair of intersections. So this one intersection, let's say V1 prime intersection Vm prime, this is simply V1 intersection Vn intersection Vm prime. Okay, so this is an intersection of sets. So this is also in B. So B is actually closed under intersection. It needs to be closed under intersection and union, meaning intersection of two things has to be union of sets, but it's even better. So it's really easy to see. And last time we have seen an example of these. If I look at vertical strips and horizontal strips in R2, they form a sub-basis. Basically anything forms a sub-basis, but they form a sub-basis of something quite more interesting, which you can think about later. Okay, so this was one characterization of sets, and besides this we have another using closed sets, and you can give a third using neighborhoods, which I will not spell out, but the concepts are more important here. So let's just define things. So a couple of definitions of neighborhoods, but for us a neighborhood neighborhood, I'm sorry, that was quite terrible. A neighborhood of x in X is an open set containing X. Containing little x, that is open set, you can call it U or something, containing X. Okay, so sometimes neighborhood is defined as saying it's a set so that there is an open set contained in this without requiring the neighborhood to be open. The two definitions lead to almost the same thing. So we'll just stick to this one. So we can define continuity, for example, in terms of neighborhoods, convergence in terms of neighborhoods, and so on. And which of the two definitions you took will make no difference. It's very easy to go between the two and the statements will be the same. This is why these two definitions have survived, because there's no better one since they're effectively equivalent. Okay, and an even more important concept is that of a closed set, which we will see a lot. So a set A contained in X is closed by definition if X minus A is open. So closed sets are complements of open sets. Now we'll see a lot of them as we go along in topology. They'll be very important in many contexts. But for now we just see the definition. It's simply the complement of an open set. And note, if we know the closed sets, we know the open sets. Okay, so given closed sets, let's call the set of closed sets F. Omega is simply X minus A in F. So we know the topology. This leads to a natural question, and which is really quite easy to answer. So which is the following. So question is, when does a collection let's look at F contained in 2 to the S form not open sets, that is not the topology, the closed sets in a topology. And the following is an immediate consequence of De Morgan's theorem. So we can basically flip the conditions which are in the definition of a topology using the complements. And so say F forms closed sets of a topology if and only if we have the following three conditions. So the first one is, well, we needed open sets to be closed under union and arbitrary union. So we'll need closed sets to be closed under intersection. So if let's call them F alpha, alpha in A is a collection of closed sets. Okay, then intersection of F alpha is closed. Okay, let's just let me write the second one. So this is, so we have flipped unions with intersections. So arbitrary unions of open sets were open, arbitrary intersections of closed sets were closed. As far as finite ones sets are concerned, we finite collections are concerned, we again flip. So finite unions of intersections of open sets were open, but similarly now if F1, F2, Fn, if it's a finite collection are closed, then F1 union Fn will be closed. By the way, this will not happen for arbitrary unions because in fact points will be closed in R or R2. It's quite easy to see that. And so every set would be a union of closed sets in most nice cases. Okay, first one we'll just briefly justify, second one is similar, and the third one is just by complementation, 5x are closed sets. Why is this? Because the complement of phi is x. So phi being closed is equivalent to x being open, and x being closed is equivalent to phi being open. So this condition 3 implies the condition for the topology and vice versa. Okay. Similarly, 1 will imply if f alpha is a collection of closed sets, this is equivalent to saying that, let me say x minus f alpha, which let's call them v alpha, as defined of this, is a collection of open sets. So now intersection of f alpha is intersection of x minus v alpha, because these are set complements, and so this is an arbitrary intersection, alpha in A, alpha in A. And De Morgan's laws will tell you that this is x minus the union of alpha in A of v alpha. Note this is open. So as a result, if v alpha is actually an open collection of open, so if f alpha are closed and it actual closed sets in a topology, then we would get that v alphas, their complements are open, so the union is open, so the complement of this is closed. And conversely, if instead you have the axiom that f alpha is that when you have a collection of closed set, intersection is closed, and you define the topology as being complements of the closed sets, okay, which is what we have here. We use this formula. Then what we notice is, given a collection of open sets, I look at f alpha, which is x minus v alpha. Okay, so this, by the way, is equivalent to saying f alpha is x minus v alpha. So we simply take a collection of open sets. Given a collection of open sets, we look at the corresponding closed sets. Their intersection is closed, and from this, in the other direction, we deduce that the original sets have a union that is open again. So this goes back and forth. It's a fairly simple switch between open sets and closed sets. As I mentioned, they are much more important beyond their role in defining topologies, as we will see through the course.